Okay, so today's speaker is Mahyar, who did his undergraduate and master's degrees in mechanical engineering at Sharif University in Tehran before coming to University of Pennsylvania, where he's a third-year PhD student working with Victor. So today he's going to be talking about his recent work in synchronization. So Mahyar?
Thanks, Alec, for the introduction. So today I'm going to talk about the title of presentation is Optimal Design for Synchronization of Oscillator Networks. So this is a joint work with my advisor, Victor and Florian Dorfler, who is an assistant professor at ETH Zurich. So I'm going to start off with the introduction about the network synchronization. Then I provide two motivating examples, AC power networks and distributed clocks. Then I move on to problem statement, which is the main body of this presentation. And I'm going to consider two general problems, frequency design and weight design problems. Then after analyzing these problems, I will move on to simulation examples. There are three interesting examples that I'm going to consider for this presentation. The first example is sparse network design. The second example is robust network design. And the third example is a phenomenon which we later explain, which is called Braess paradox. And then we conclude this presentation with conclusion of future work. So, okay, so what are the ingredients of synchronization, network synchronization? So, as the name implies, we have a collection of dynamical systems. So, they are the trajectories are evolving independently over time. But if we allow them to interact over a communication graph, an interaction graph, then we get a coupled network dynamical systems that described here. So the first term, Fi, Xi, is the individual dynamics of each of the nodes. And this interaction, this summation is the interaction of each of the dynamical systems with its neighbors. So we have a dynamical systems, a couple of dynamical systems, and a connection graph. So now I can define the notion of synchronization here. So we have a complete synchronization notion, which means that we get complete synchronization for this network dynamical systems when all the states of the dynamical systems, when all the trajectories converge to the same trajectory over time. This is the definition of complete synchronization as opposed to partial synchronization. So we have different notions for partial synchronization. I have stated the three definitions, particular definitions. There may be more definitions in the literature. So the first one is we have just only complete synchronization on ith coordinate, let's say, on the ith coordinate of the trajectories, or a subset of the coordinates. Another notion is complete synchronization on the velocities of the trajectories, not the state vectors, right? So this is the synchronization manifolds when all the velocities are equal to each other. And the last definition is just complete synchronization in a local sense, meaning that not all the nodes, but a subset of the oscillators synchronize their trajectories together. So we have these three different notions of partial synchronization. So as you can see, this network dynamical system is very general in the sense that this Fi is arbitrary. It's not arbitrary. I mean, we haven't provided a specific structure for these functions as well as these coupling functions. So we have to be more specific. And the specific dynamics that I'm going to consider is this Kuramoto oscillator networks. And what is this dynamics? As you can see here, so suppose that we have a graph, and at each node of this graph, so suppose that there is a vector of constant magnitude which is rotating with some angular velocity, right? And this theta I represents the angle of this vector, right? When these oscillators are decoupled from each other, they have different natural frequencies, so they start to rotate with different angular velocities, so they will have different phases. However, if we connect them through a graph with this kind of a specific coupling, a sine function, and an undirected graph, which I explain later, so it is possible for the phases to synchronize. They start rotating with the same angular velocity asymptotically, right? So I'm going to focus on this particular dynamics. Why? Because this dynamics appears in many practical settings, in many technological systems, as well as biological systems. So the first and most important technological application is AC power network. So in AC power network, I have provided a cartoonish illustration of a power network. So in this network, the nodes are either generators and load buses. So the generators generates power, and the load buses consumes power. And what is the graph here? The graph are just physical transmission lines that connect all of these generator and load buses together, right? And each transmission line is described by an admittance, which is the sum of reactance plus the imaginary times the susceptance, right? Okay, so the governing equation of the generators is this first equation, right? It's a second-order dynamical system. This is the inertia of the generator. This is the damping term. This PMI is a constant representing the power injected to the network via this generator. And this is this summation is simply the transmission of real power along the transmission lines. And the second equation describes the power flow in load buses. It is the same as generators, except for that we don't have this inertia term anymore, right? So as you can see, this dynamics, the right-hand side of this dynamics, these two coupled dynamics, is the same as the Kuramoto dynamics, except for this term, extra term. But as we see later in later slides, this term doesn't matter in our analysis because we are going to work with the right-hand side. And also it is true that this additional dynamics, this second-order dynamics, only affects the transient behavior and not the steady-state behavior that I'm going to analyze in this presentation. So, right, this is the dynamics of power grid, which is the same as Kuramoto model. And what are the weights of the graph? The weights of the graph are the magnitude of voltage at, for example, generator or load bus I, times the magnitude of voltage at generator or load bus J, times the susceptance of the transmission line, as you can see here. This is the first example. There are other models for AC power network, but this model is a structure-preserving lossless AC power network model. So there are two restrictions, there are two assumptions that I'm not going to give details about, but I can be more specific if you want. The second example is the clock synchronization in decentralized networks. Here, my nodes are a set of analog clocks. They want to do some distributed computation, and they have some internal clocks. So the internal clocks are supposed to have the same natural frequency because the processors are supposed to be the same, right? But because of manufacturing imperfections, this period, T nominal, is not the same for all the processors. There's some uncertainty, there's manufacturing imperfections that causes these natural frequencies to not to be identical for all the processors, right? So what is the consequence? The consequence is that if the clocks starts individually integrating the time, integrating natural frequency, they will get different phases over time, and it degrades the performance of the decentralized network in computation. So one way to synchronize these analog clocks is using this diffusive coupling like Kuramoto model, because for example, if you look at this, what should node I do? It should measure the phase difference across its neighbors, which can be done by phase detector. Then it passes this phase difference through 2π periodic odd function, and then it takes the convex combination of these output functions, and then it subtracts the result from the natural frequency, and then it starts integrating. And we'll show that these phases will converge together, not completely, but partial synchronization will be achievable. This is only one way of synchronizing the clocks, by the way. So these are two motivating examples. Now, I'm going to go to problem statements, so I should be first more specific about the dynamics. So I have a weighted, connected, undirected graph G described by a set of nodes V and edges E. So I have n nodes and m edges, and I have a weighted adjacent symmetrics A. This A fully characterizes this graph, both the structure and the weights of the connections. We can have an alternative representation of this graph by incidence matrix. So what is incidence matrix? Incidence matrix has as many columns as the number of edges, n by m. So first I label all the edges from 1 to m, right? 1, 2, 3 to m. And for example, and I will assign some arbitrary direction to each edge. So for example, if I connect node I to node j via edge number e, then I look at the corresponding column number e of matrix B. I set the ith coordinate of this column vector to +1, meaning that I is source, and bje to -1, meaning that j is the sink. This assignment of direction is arbitrary because there will be symmetric calculations involved, so all the plus minus signs will cancel out, so it doesn't matter what direction I choose here. So after labeling all the edges, I put the weights, the labeled weights, I stack them in a vector W, which is an m-dimensional non-negative vector, and I can represent the Laplacian matrix as L equal to B diagonal of the weight vector times B transpose. So this might be very trivial and familiar for most of you. So this is the Laplacian matrix, which is symmetric matrix. So, and if I stack all the natural frequencies in my dynamics in a vector of omega, so this was my dynamics as I stated in the first slide. Now I represent this dynamics in matrix form. So I have a Kuramoto model, which depends on 3 parameters: incidence matrix, weight vector, and natural frequencies. And this is the dynamics in vector form. Theta dot equal to natural frequency minus B incidence matrix, the diagonal matrix of the weights, times sine of this vector, B transpose theta, right? Okay. So we can have different perspectives on this dynamics. The first perspective is energy perspective. Actually, the total energy of the system is this summation. As you can see, it involves 2 summations. The first summation involves the term that it is a kind of consensus term, nonlinear consensus term, that tend to synchronize all the theta i's. And the second term is a repulsion term. It tends to move away, to drive away all the phases from each other, right? So if I want to view this problem as a distributed optimization perspective, actually I have a global objective function, which is an affine function, which is a hyperplane. The local objective functions are just some constant times the state of that local node, and this becomes my cost function to be maximized. So if we perform a distributed gradient descent on this objective function, it can be fully distributed. So theta I becomes omega I minus this summation, which is the Kuramoto oscillator model. So this is interesting for people who work on distributed optimization or optimization in general. Now let's go to the definition of synchronization for these Kuramoto oscillators. So as you recall, we have 2 kinds of synchronization: complete synchronization and partial synchronization. So for this dynamics, complete synchronization means that all the phases converge asymptotically to each other. So there's no gap between the steady state phases, which we call this situation phase synchronization. Another definition for partial synchronization is that all the phases converge to a constant value, but they don't converge. They don't make complete synchronization. So there's a steady state gap between the phases. Okay, so the synchronization trajectory, the frequency synchronization trajectory, it can be shown to be described by this equation. So the first term is a time-dependent term, is omega s, which is the average of the natural frequencies, which is the synchronized frequencies, times t, which is the time, times the vector of all bonds. So this is the consensus term, plus some constant theta star. This is my synchronized solution, right? So these three figures show different behaviors of this dynamical system. So the leftmost figure shows that we have desynchronization, all the phases diverge. The second figure shows that all the phases achieve frequency synchronization, so they converge to the same slope, but they don't converge to each other. There's a steady-state gap. And the last one is complete phase synchronization, where all the phases also agree with each other. Yes?
What's written in the labels of the axis?
These are the angles, phases, theta i's. For example, for a network of 20 nodes, I guess it was 20 nodes. And this is time. Sure. So you can see that we have a spectrum of different behaviors. So for quantifying this behavior, we define phase cohesiveness for Kuramoto model described by B, W, and omega as the edgewise maximum asymptotic phase difference across the edges, right? So intuitively, it is the maximum gap that you can see in the steady-state phase along the edges, right? So which is in vector form is the infinity norm of B transpose theta star. Theta star is the constant term here that appears in the synchronized trajectory, right? Sure.
What's the synchronization trajectory?
Synchronization trajectory is a trajectory that all the phase, I mean, this is, the definition is that the limit of, if you consider this vector form, this theta will converge asymptotically to theta s. So yeah. So this is depicted here. So all the phases asymptotically have the same slope. This is a vector of 1, right? So they will increase with the same rate, but there is a gap, steady-state gap across them. Yes. No. Across all the edges.
So it's like the maximum minus the limit here on the spots.
No. So you have m edges, right? So you have m such phase differences. You take the maximum across all the edges, right? Perfect. Okay. So I want to see how. Is there any question? So I want to see how can I evaluate the performance of a synchronous solution. So it depends on how I should view this problem. For example, if I care about the transient behavior, so the transient behavior is the ability to resynchronize after perturbation. So after all the phases converge to, for example, this synchronization manifold here, so due to some perturbations, for example, load imbalances in the power network, or so any other perturbations, noise, disturbance, so these steady-state phases are perturbed, and they have to resynchronize. They have to go over this transient phase again. They have to resynchronize again. So this is the notion of transient behavior, and people characterize this by the algebraic connectivity of the connection graph, right? So this is similar to, for example, maximum fastest mixing Markov chain, and which is related to the algebraic connectivity of the connection graph. So there are many papers that stating conditions for synchronization regarding this lambda 2. For example, one sufficient condition which is stated in this paper is that if the lambda 2 of my graph is greater than the maximum natural frequency difference across the edges, I will get synchronization, right? So I get this middle figure. Yes. But if this is less than this value, we cannot say anything. This is still a sufficient condition. But if I want to care about the steady-state behavior, so in the steady-state behavior, as we saw in the previous slide, we can characterize by this phase cohesiveness, which is the maximum phase difference in the steady state. so which is phi of B, W, and omega. So this phase cohesiveness, it can be seen that this phase cohesiveness, when it approaches to 0, we get complete synchronization. And in practical settings, this phase cohesiveness has a meaning. For example, in power networks, it is a thermal limit constraint for power networks. For example, they say that this phase cohesiveness should not exceed, for example, 25 degrees in power networks, right? So the main question that we are going to cover in this talk is how to optimize the steady-state performance of a synchronized solution. What do I mean by that? I mean that we consider this phase cohesiveness as our objective function, and I use these parameters B, which is the incidence matrix of my graph, which encodes the structure of the graph, these weight vectors, and the natural frequencies as my decision variables, right? So, okay. So I'm gonna for doing this optimization, first I need to develop this objective function. What is phi? I don't have a closed form solution for phi, as you remember here. It is the infinity norm of B transpose theta star. I don't know theta star. I should find this explicitly in terms of omega, W, and B, right, in order to do the optimization. Okay, so recall that the synchronized solution is this, and the phase cohesiveness is B transpose theta star, the infinity norm, so we should find theta star. If I substitute this synchronized solution in my dynamics, I get this fixed point equation, right? BW sine of B transpose theta star should be equal to omega minus the average of omega times the vector of 1, right? And since we have a periodic dynamics, we just consider theta stars, which is constrained in the n-dimensional cube from 0 to 2 pi, right? Without loss of generality, I can assume that this omega s is 0. When this omega s is 0, it means that the average of the natural frequencies is 0. So what do I mean by that? If the average of the natural frequencies is 0, this means that this synchronized solution is just a fixed point. It doesn't involve any time-varying term anymore. So I'm by this assumption, I'm mapping the synchronized solutions to fixed points in order to be able to do some local stability analysis. There's no time involved, right? So this is a fixed point equation of my Kuramoto dynamics. So I want to find theta star. So from this equation, it can be seen that I want to solve for sine of B transpose theta star first. So sine of B transpose theta star is this first term plus this second term. So what are these terms? So the first term is a particular solution. If you substitute this particular solution into this fixed point equation, you can see that it satisfies, right? What is L? This is the pseudo-inverse of my Laplacian matrix defined here. And the second term is due to the existence of cycles in the graph. I mean, because this matrix B is not full rank, we are going to have some homogeneous solutions here because of the cycles in the graph. Okay, so we haven't. So if I didn't have this term, it would be nice because now I have the sine of B transpose theta star in terms of all the network parameters, but I still have this y here. I cannot find, I still need to find this y here, right? Okay, so actually the problem is that finding the number of stable theta stars, solving this equation completely, finding those y, it has been shown in this paper, as a recent paper in 2015, that is an NP-hard problem. So we cannot characterize this theta star in terms of these parameters, B, W, and omega, right? But this is not the end of the story. There is a criterion that has been proposed in this paper by Florian, which is a collaborator in this work, that helps us to get rid of this difficulty. So what does this criterion says? This criterion says that for a Kuramoto model described by these three parameters, if this particular solution, recall that this is the particular solution, B transpose L pseudo inverse omega. if the infinity norm of this particular solution is less than sine of some angle from 0 to pi over 2, then I get a unique theta star with gamma star level of phase cohesiveness. What does it mean? It means that I have this upper bound for phase cohesiveness. I cannot get equality because it's NP hard, but I can get this inequality. So the sign of my phase cohesiveness is less than or equal to infinity norm of the particular solution in the previous slide, right? So this upper bound is not crude, it's not very bad. I mean, it's an accurate upper bound for phase cohesiveness, and it is sharp for power networks, meaning that they are almost equal. But the bad news is that there's no analytical proof for this. So this has been suggested by the author by means of there's some justification for derivation of this particular solution, but there's no analytical proof, and the proof is based on Monte Carlo simulations. So, for example, this is the table provided in this paper. So the authors have taken these 10 test cases of IEEE power grids. So for each of these 10 test cases, they have realized 1,000 instances of natural frequencies. They change the natural frequencies, they run the dynamics, they measure the phase cohesiveness, and they evaluate and they check the validity of this inequality. So, for example, for this, so this is always true, and this is the gap in this inequality. As you can see, it's almost zero.
Is that the average over the 1,000 instances or worst case?
It's the worst case. As you can see, we have max here. Yeah. Okay. So I'm going to use this, in this work, I'm going to use this inequality in order to do the optimization. So what are the network design problems that I'm going to consider? The first problem is frequency design, in which I have fixed the structure of my graph. I don't change the weights. I just design the natural frequencies. I assign a cost function to these natural frequencies. So, and I have a convex design set, and I consider two problems. So first, I guarantee a certain level of phase cohesiveness with minimum cost design. So I minimize this subject to some constraint on the phase cohesiveness. And the second set of problems has the same structure, but here the natural frequencies are fixed, and I design the weights, which can be generalized to the case of designing B as well. So I can change the structure of the graph. I can design the weights. So I consider these two problems. So the first set of problem is frequency design. So these are this is the statement of the problem. So the first thing is that I have a connected undirected graph G with incidence matrix B. You give me this matrix B, and you give me the weights of the graph, the weights of the edges, W0, and you give me a convex frequency tuning function, G, and a feasible design set and a fixed budget on modifying these natural frequencies. And I solve this problem. So I want to find omega star such that my phase, the upper bound for the phase cohesiveness is minimized subject to budget constraint. And this, as you recall, this is my assumption that the average of natural frequencies should be 0. So if I solve this problem and I get this omega star according to that criterion, then my phase cohesiveness, the maximum gap between the phases, will not exceed this upper bound. So this problem is not. So this problem is trivially convex because this G is convex by assumption, and this is an infinity norm of an affine function of omega, which is also convex. So I get a convex problem here, right? The other way around is this is a more meaningful problem that instead of minimizing the phase cohesiveness, I'm required to keep the phase cohesiveness below some certain level. So, for example, I should keep this phase cohesiveness below, for example, 25 degrees, and I want to design omega with minimum cost, right? So again, if I design and the resulting optimal point is omega star, then my phase cohesiveness will not exceed gamma d by that criteria. These are the two problems for frequency design. This is one quick application of this frequency design problem. So, for example, suppose that I have an AC power network, right? Recall that in AC power networks, the natural frequencies of the Kuramoto oscillators correspond to power generation and consumptions, right? So, so these natural frequencies are the powers generated by each generator and power consumed by the load buses, right? So here's the scenario. So we have a power grid. So because of uneven distribution of power across the network, because, for example, new generation units are, for example, placed in, for example, coastal areas, so or due to some other constraints, the power distribution across the network are not even, right? This causes the phase cohesiveness to increase and pass a threshold that is the desired level of phase cohesiveness. So I have a power network. Omega 0 is the current power distribution, and my phase cohesiveness is greater than gamma d. I want to redispatch the power. I want to perturb this power generation to guarantee that the phase cohesiveness of the resulting power network is less than gamma d. Now we can cast this problem as this frequency design problem. The natural cost function here is the norm 1 of my perturbation, which means that this is the amount of displaced power across the network. So I want to minimize this displaced power subject to this constraint, which guarantees that my phase cohesiveness will not exceed this threshold. And for the load buses, I cannot change the powers. I'm just doing the manipulations on the generators, right? So these perturbations should be equal to 0 at load buses, and of course, the power due to conservation of energy, the sum of the power perturbations should be 0 across all the nodes. Okay, so this is the second part of the problem, which is more interesting and more practical. So now I want to fix my natural frequencies, and I want to design the weights. However, this is a practical observation that my natural frequencies, for example, in power network is the power consumption and power generation, so they are not given to you. They are not known, or they are uncertain, or they can fluctuate. So the difference here is that I still have a connected undirected graph G with incidence matrix B, but my natural frequency is not known, but I know that it belongs to a convex uncertainty set, right? And I am given a weight tuning function for tuning my weights, and I have a feasible design set, and I have a fixed budget for tuning the weights. So I take a minimax approach here. So what I want to do, I want to first, so this is the upper bound, again, this is the upper bound for phase cohesiveness. I take the worst case phase cohesiveness for the natural frequencies in this uncertainty set, and I minimize the maximum value of this, subject to budget constraints, right? If I do this optimization problem, then I have guaranteed that my phase cohesiveness is less than or equal to this value, right? So how can I solve this min-max problem? So I use robust optimization framework. So how can I do that? Okay, so the first step is that, so I want to solve this problem. So first I introduce a slack T. So I minimize T subject to the max to be less than or equal to T, as you can see here. So I minimize T subject to this budget constraint and this max to be less than or equal to T, right? So my constraint involves an optimization problem itself. The main optimization problem is with respect to the weights, but the constraint is an optimization problem with respect to omega. How can I handle this problem? Let's take a look at this blue term. So the next step is that I break this max of infinity norm into these two inequalities. So the max of the infinity norm of this vector using this identity is the maximum of the components of these to be less than t plus and minus sign, right? So I break down this max into two inequalities for k equal 1 to n. Okay, so now I want to look at these two terms individually. So let's take a look at this term. So I construct the Lagrangian of this function. So we are maximizing with respect to omega, and my weight is fixed, right? So I construct a Lagrangian, and my constraint set, I consider this constraint set. So it means that I don't know the natural frequencies, but I have an upper bound and lower bound for the natural frequencies, right? So I construct the Lagrangian function, which is the objective function that I'm maximizing plus the augmented term by the constraints, right? So these are my Lagrangian multipliers, which are non-negative, and this is my the last Lagrangian multiplier for this equality constraint. So if I rearrange the terms, I get a Lagrangian, which is an affine function of the natural frequency, right here. So this is a constant vector times the natural frequency plus a constant term. So the next step is to develop the dual function. So the dual function for this Lagrangian is if the coefficient of the natural frequency, if this coefficient is equal to 0, my Lagrangian is constant, which is equal to this. Otherwise, I can push it to infinity, right? So this is my dual function. And the step 5 is using Vic duality. Vic duality says that this maximization with respect to omega is always less than or equal to my dual function. So as you recall, this the original constraint was that the max of this term should be less than or equal to t. So it suffices that I put the upper bound, which is the dual function, to be less than or equal to t, and then substitute this g of k less than or equal to t back into the equations. So by this way, I have eliminated this omega in my optimization problems, right? So I have introduced some variables, extra variables, and I get this optimization problem. Now my optimization variables are this t, my weight vectors, and my Lagrange multipliers, the upper and lower bounds of the natural frequencies, and I can solve this optimization problem, right? Okay. Okay, so one more step. This problem is still not convex, as you might agree, because of this pseudo-inverse operation here. We have my optimization variables, one of them is W, and here I have B diagonal of W, B transpose pseudo-inverse, right? So I got rid of that uncertainty, but I'm still not convex. So the convex I wanna develop the convex relaxation of that problem. So for convex relaxation, we use this short complement lemma, which says that, for example, suppose that I have this minimization problem, which is an STP. So this matrix being positive semi-definite means that this L bar, which is my optimization variable here, should be at least as big as the inverse of this block, right? So when I minimize a trace of L, I can recover the pseudo-inverse of this matrix here. So I used this lemma in my previous problem to get a convex relaxation here. So this constraint is my budget constraint. These 5 equations handle the uncertainty. And these LMI pushes L bar, hopefully pushes L bar to this, the pseudo-inverse of this. And I replace the pseudo-inverse by L bar here. Right? So this is a regularization relaxation. Yeah. So one drawback with this optimization is that this alpha should be found with trial error. So I cannot arbitrarily assign alpha equal to some constant and do the optimization. I should always check that if this L bar is becomes equal to the pseudo-inverse of this matrix, right? So this is a trial and error approach for finding this alpha. and I solved this problem, network weight design problem. The last problem has the same story, except for that I swapped the constraint. So in this problem, I want to keep my phase cohesiveness. I want to guarantee a certain level of phase cohesiveness subject to while minimizing my cost of tuning, right? Okay, this is the end of the theory that that we are going to some examples. The first example is, I'm given a set of oscillators with natural frequencies, so there's no uncertainty here in this example. So I'm given these natural frequencies, and I'm given a desired level of phase cohesiveness from 0 to pi over 2, and my task is to design the sparsest graph that can guarantee this phase of phase cohesiveness, right? So in compact form, the optimization problem that I'm going to solve is this problem. So I want to minimize the L0 norm of my weight vector subject to this constraint, that phase cohesiveness to be less than or equal to gamma d, right? So what is the L0 norm? Is the number of non-zero elements of my weight vector, right? So the simplest way to handle this problem is to just relax this L01 norm to L1 norm, because it's a sparsity-promoting norm. However, it doesn't give a really sparse solution. For example, if I have a graph with 200 possible edges, I get a graph with, for example, 160 edges. So it's not really sparse. Many weights are close to 0, but not equal to 0. So in order to avoid this issue, I used an algorithm taken from this paper by Emmanuel Candace, which is a reweighted L1 algorithm. What does this do? Actually, in the first step, I just solved the L1 problem. So I reweight the weights. I reweight the weights with some coefficients initially set to 1. So I solved this problem in the first iteration, and I update the penalizing terms here, the coefficients here, according to this rule. So what does this rule say? So this rule says that, for example, for the weights that are close to 0 at this iteration, I increase the penalizing coefficient in the next iteration, because it is tending to go to 0, but it is not pushed enough. So in the next iteration, I increase the weights. So I push it further into 0, and I do this iteration for example, for k iterations, and I get a sparse solution. So this is the result of the simulation, for example, for a graph of 20 nodes and 190 Boolean edges. So I start the iterations. So the x-axis is the number of iterations. The y-axis is the percentage of sparsity. So, for example, the first iteration gives me, I think it was 2% sparsity. Then at the 10th iteration, I get around 70% sparsity. And at around iteration 20, I stabilize with 31 edges. So the amount of sparsity, the percentage of sparsity will be around 84%. And I have set the desired phase cohesiveness to 78 degrees, and my natural frequencies is linearly placed from -1 to 1 in this example. Yeah, sure.
Yes, good question. Maybe I misunderstood you, but so the phase cohesiveness depends on the graph, like the maximum across the edges of the graph. Is this correct?
Yes, it depends on the structure of the graph, it depends on the weights of the edges, and depends on the natural frequencies.
Okay, but so if I want to minimize the cohesiveness, why I don't just give you an unconnected, like a graph with no edges, then it will be 0. I don't know.
No edges.
Yeah, no edges
If you
at all.
don't have no edges, they will diverge.
But there's no, so you're computing the maximum across the edges.
We should readapt this definition. I know what you mean. I mean, they don't stabilize to a constant value if you have no edges, right?
Okay, but the cost is still 0 because it's a maximum across an edge.
Yeah, this is but it doesn't make.
It's connected, right?
Yes, I assume that the graph is connected.
How do you enforce it?
In my equations, enforce this in this LMI. I forgot. That's a very good question. So if my graph is not connected, this matrix happens to be positive semi-definite, and this LMI doesn't work. Yeah. Thank you for mentioning that. So this is the first example. The second example is the robust network design. Now I have a frequency uncertainty set. So I don't know the natural frequencies. I have the lower and upper bounds. And I want to, again, to achieve a certain level of phase cohesiveness. I want to guarantee, and I want to minimize the sum of the weights. So my cost function is the norm 1 of the weights subject to this constraint. The simulation data is I have 39 Boolean edges. I want to modify the weights of these edges. And I have 20 nodes. And my desired phase cohesiveness is 60 degrees. And again, my natural frequencies, the nominal natural frequencies, are linearly placed from -1 to 1 and has 40% component-wise fluctuation. Right? So the resulting cost function is, so if I don't have any uncertainty, if I know the exact value of the natural frequencies, I get this cost, which is 22.7. And if I have 40% uncertainty, I have to pay the price. And the infinity norm of 1 will be equal to 27.2. And we can analytically check that the maximum phase cohesiveness by doing some linear optimization, as I stated before, that it is always less than 60 degrees. And this is so what is this figure? So I have realized 200 instances of this natural frequency in this convex set. I have run the simulation. I have measured the phase cohesiveness. And this is the value of the phase cohesiveness. And that 60 degrees, the red line, is my threshold. As you can see, it doesn't pass the threshold, which means that it is robust. And the last example is the Braess paradox. So Braess paradox happens in many contexts, but in the context of power networks is this. So recall that the energy function is has two terms, an attraction term and a repulsion term, right? So this tends to synchronize the phases. This tends to drive away the phases. So our intuition says that if I increase the weights here, I'm going to get better synchronization, right? So by increasing these AIJs, right? But this is not true. What I mean by that, so for example, this is the power network of New England. This is the cartoonish network, so this is not a real geographical data. So taken from this paper. So this power network synchronizes with these phases. Everything is good. Now I start adding this edge in this network. Then I suddenly get desynchronization. This doesn't agree with our intuition that because I'm tying the oscillators together, but everything gets worse. So this problem has been studied just numerically, as you can see in this figure. They just add an edge, and then they simulate the dynamics, and then they conclude that this edge is very dangerous. You shouldn't add this transmission line. But this phase cohesiveness that I talked about today, we show that this can be used as an analytical tool to study this Braess paradox. So this is a very simple example. So I have this power network, small power network example. The greens are generators, and the blue nodes are power load buses. So I have synchronization here, and all the weights are equal to 1. I have two scenarios. First, I start increase this capacity line, and the second scenario, I add this line. So I want to see what happens to the phase cohesiveness function, to the upper bound, right? So the idea is to use this phase cohesiveness as a proxy for predicting cascading failures. So as you can see, so this is for the first scenario. As I start manipulating this transmission line, the initial value is the initial value of the capacity is 1. Once I move away from 1, either decrease the capacity or increase the capacity, my upper bound goes beyond 1. And I didn't mention in the slides that if this upper bound goes above 1, it is equivalent to desynchronization. So below 1, we have synchronization. Above 1, we have desynchronization. And as you can see, only at this capacity, which is equal to 1, I get synchronization. No other point, right? The second scenario is just adding this capacity. So when I add this capacity again, I start from 1, the threshold of stability, and no matter how strong this connection is, I exceed this threshold and I get instability. These are the numerical simulations of the phases for different scenarios. So these two figures. This figure is on the left-hand side here when the capacity is less than 1. This is for capacity equal to 1. This is for capacity greater than 1. And then I redesign the network with this framework that I told you before, and I get this result, better synchronization. So yeah, this is the last slide. So I studied this Kuramoto dynamics. I defined phase cohesiveness as the objective function, and I designed these natural frequencies and the weight vectors. And these are the future works that I want to explore the correlation between lambda 2 and phase cohesiveness. So if I push I want to study if I push these angles together in the steady state, does it have anything to do with the lambda 2 as well? Is there any positive correlation between these two? The second question, which is more appealing than the first one, is that, so I define this basin of attraction for any fixed point theta star, right? The basin of attraction is the set of all the initial conditions for which, if I start from this initial condition, I converge to the optimal point. So there's a region surrounding this optimal point that constitutes the basin of attraction of this fixed point, right? So I want to see that if I decrease, this is the typo, if I decrease the phase cohesiveness and if I make it, for example, push it towards 0, what happens to the volume of this basin of attraction? Then if this correlation is, if this implication is correct, then by means of this phase cohesiveness, I can also increase the basin of stability, which is really important for power systems community. And that's it. So any questions? Yeah.
So in the last example that we had, what happened is that there was an addition of a connection, right? And then what you did is that you redesigned, you rerun your optimization, right?
Last example doesn't involve any optimization. So I just analyze, I just compute this infinity norm for different. For example, I add the transmission line. I recompute this infinity norm to see what happens. And yes, it doesn't involve any optimization. I want to show that this is a good measure of predicting that whether we get stability or instability when we add a new line.
My question is, if you run your optimization, let's say, using waves,
Right. What do you mean? If I run my optimization, yes. That's a very good point. So I get the stability by this constraint. The stability is guaranteed if my phase cohesiveness is between 0 and 90 degrees. So if I put any point here, any angle here which is less than 90 degrees, strictly less than 90 degrees, I get the stability at the same time. So they are completely interconnected. So it doesn't mean that I get, for example, 60 degrees of phase cohesiveness and get desynchronization. It cannot happen by structure. But that's a very good question. The stability threshold? Yeah. So it can be let me go back. So this is my fixed point of this dynamical system, right? This equation, right? So if you do a local stability, if you linearize the dynamics around this point, right, you can conclude that if phase cohesiveness is between 0 and 90 degrees, meaning that if the sign of B transpose theta, the infinity norm, is less than 1, I have guaranteed stability. So this is a proxy for, I mean, this is a threshold. Value equal to 1 means my phase cohesiveness is 90 degrees. So if I'm below 90 degrees, I have guaranteed stabilization. If I pass this threshold, I get instability. I think the intuition is that when you add an edge, I can say just the flows start to redistribute, and this redistribution can, for example, increase the flow of some edge in some part of the network. So, for example, you have two separated components, for example, connected by a single edge. If you perturb one of the components, then, for example, some flow should pass this edge and this redistributed flow can exceed that threshold. This is the intuition. The first intuition is that no, we should get better synchronization, but it doesn't agree. Okay, thank you.